This bridge has the longest span of any cable-stayed bridge in the world. It faces challenges that would destroy an ordinary bridge. The water is too deep, the seabed too soft, and an earthquake fault line cuts through the middle. How do you design a bridge to overcome nature's worst? What does it take to build one of the world's mega bridges? This is the Gulf of Corinth in Greece. It's deep, wide, and long. Great attributes for marine traffic, but a nightmare for those traveling by land. The Gulf of Corinth virtually chops Greece in two. The only land route between southern Greece and the rest of Europe is 240 kilometers east. Bridging the Gulf has been a goal for more than a century, but it has never been possible, until now. The Rion Antirion bridge is the first ever to cross the Gulf of Corinth. It clears the water by more than 50 meters, leaving plenty of room for even the biggest ships. The design of the bridge looks deceptively simple. 368 sleek cables, 4 conical towers, and a yellow ribbon of roadway that glows at night. But the truly amazing thing about this bridge is how it came to be built here in the first place. Challenges of building here were so mind-boggling that they stumped engineers for decades. The biggest challenge was earthquakes. Bridges had been built in earthquake zones before, but this bridge had to cross an active seismic fault line. On top of that, the water here is extremely deep, 60 meters. No other bridge had been built with foundations to that depth. It would take a daring plan to overcome these hurdles. In April 1996, the only way to cross the Gulf of Corinth was by ferry boat. In perfect weather, the journey took 45 minutes. A bridge would reduce that to 5. So for decades, the Greek government had looked for new bridge designs. The bridge would have to be extraordinary, but designers' options were limited. Virtually all bridge designs are based on just 4 types: beam, arch, suspension, and cable stayed. Choosing the right starting design is always crucial. The main criterion is length. The longest bridges in the world are beam bridges, but this design wouldn't work in the Gulf of Corinth. In a beam bridge, the flat road spans must be supported from below approximately every 100 meters. Hundreds of support piers like this would block major ship traffic. An arch bridge can stay clear of huge ship traffic, but to span the Gulf of Corinth would require an arch bridge 4 times bigger than any built before. This design was deemed too risky. A suspension bridge can leap the longest distances of any design. Enormous cables stretch from one shore to the other, then shorter cables hang down to hold the roadway. But all these steel cables make suspension bridges expensive. They cost hundreds of millions of pounds. Greece simply couldn't afford to build one. This left just one possible option: a cable-stayed bridge. In this design, there are no expensive main cables. Instead, the smaller cables hang directly from towers. But no cable-stayed bridge built to date would be able to survive the demands of the Gulf of Corinth. The most promising plan came from a French company, Vinci. Vinci's design would attempt to build the world's longest continuously suspended road span. It would require 4 consecutive towers, something that had not been tried before. A 2,200-meter roadway would then hang from the giant towers. The towers would bear the entire weight of the bridge, so they would have to be planted on extremely solid ground. At 15 meters, they found only silt, sand, and clay. 90 meters down, they still hadn't hit solid ground. There was no bedrock even at 450 meters deep. This was a major setback. Engineers couldn't build record-setting bridge towers without sturdy ground to support them. During earthquakes, the loose seabed here liquefies, which could mean the towers would tilt and destroy the bridge. Vinci's design was not going to work, so the engineers returned to the drawing board and emerged with an even bolder plan. They would strengthen the sea floor by embedding 30-meter-long metal cylinders, hundreds of them under each tower. In an earthquake, these pipes should hold the soil firm. It had never been tried before. No one even knew exactly how to do it, but the plan was convincing, and Vinci won the contract. No sooner had they done so than they were faced with an even bigger challenge. The Greek government insisted that the bridge must be completed within 5 years, or the builders would have to pay huge financial penalties. Construction began in the summer of 1999. The team's first hurdle was to invent a machine to install the soil reinforcement pipes. Each pipe was a massive 30 meters long and 2 meters wide. They needed to drive the pipes with precision, so they required a floating platform that was perfectly steady. At normal depths, builders can use a 4-legged barge. The legs extend to the seabed and hold the barge steady against currents and waves. But this would not be possible in the Gulf of Corinth. The seabed there was too soft, and the legs would not reach the deep bottom. So the engineers invented their own platform. They started with a barge called Lisa. First, the crew removed the legs and replaced them with enormous chains. Each chain had an anchor made of concrete slabs, 680,000 kilograms worth. The crew then sailed the barge into position, lowered the anchors, and pulled the chains tight. Now the barge was held rock steady. But having a stationary platform was only part of the solution. They then had to precisely guide the massive pipes through 60 meters of water. To do this, workers fitted Lisa with an enormous frame. The frame held a guide tube that could be moved to exact locations using GPS. A hydraulic hammerhead then picked up one of the pipes, and a crane moved the hammerhead and pipe to the guide tube. Even at the surface, it was difficult to maneuver the 2-meter-wide pipe into position and thread it into the guide ring. Once in place, the pipe had to be rammed into the seabed. The hydraulic hammer delivered 73,000 kilograms of force with each blow. The pipes might have strengthened the seabed, but they also created a new problem. The towers needed to rest on a perfectly flat surface, so the builders had to add a layer of gravel, 3 meters thick. The problem was how to smooth an enormous pile of gravel 60 meters underwater.
You cannot send people diving at that depth without a lot of care. They cannot stay very long. They cannot wear very much. So you forget it. This is not the way.
So the engineers developed a different system. They used the guide tube. Operators placed the bottom of the guide tube exactly where they wanted the top of the gravel to be. Then they poured the gravel into the pipe. As they moved the pipe, the gravel poured out at exactly the right level. Sonar scans showed the gravel level was accurate to within 5 centimeters. While the seabed was being strengthened and leveled, the construction crew tackled its next big challenge, the towers. First, the foundations were built on shore. They would be larger than any other bridge foundations ever built. 1.5 times the size of a football field. The crew started the foundations by laying down a dense base of steel reinforcement bars. It took close to 2 million kilograms of rebar to make the framework for just one tower foundation. Next came nearly 19 million liters of concrete. But the crew couldn't just pour it on. The dense web of rebar interfered with the flow and created air pockets. So workers had to force huge vibrating wands deep into the wet concrete to compact it and make it stronger. At this stage, the foundation looked like an enormous flying saucer. But unfortunately, it was far too heavy to fly. The crew was going to have a problem moving it out of the dry dock. The bridge foundation alone weighed a staggering 64 million kilograms, too heavy to lift. So engineers designed the colossal structure to incorporate 32 air compartments that allowed it to float. In order to float the foundation, the construction area was completely flooded. But even then, they needed an engine with 25,000 horsepower to move it. So the engineers brought in an icebreaker from Norway, something not often seen in the Mediterranean. The foundations extended 12 meters underwater. But now came the real challenge, to transform them into towers 230 meters tall. If the workers had built the entire towers in the shallow dry dock, they would have weighed too much to lift. So the towers needed to be built while they were floating. As construction continued, observers witnessed endless cement trucks, barges of supplies, and hundreds of workers. But they saw very little actual progress. The towers never seemed to get any higher. This was because as they grew taller, they also grew heavier and sank even further under the added weight. The tower's real height was never visible. In May 2001, after a year of construction, the first floating tower was ready. Now the crew had to relocate it and sink it into place. The margin for error was just 10 centimeters. It took 3 tugboats to tow the huge structure into position. Then workers slowly added seawater to the 32 compartments in the foundation. The enormous unit began to sink. Its precise placement on the seabed was critical. The positioning was monitored by GPS.
That was a bit tricky in our mind. We were a bit afraid when we started this operation.
Centimeter by centimeter, they lowered the tower towards the floor of the Gulf. Winches on the tugs guided it into place. Everything was going perfectly, until the moment before the foundation touched the bed of gravel. Suddenly, the anchor to one of the tugboats slipped. The entire foundation moved 30 centimeters off target. 3 times the acceptable margin for error. To reposition it, the crew would have to raise it and begin the process over again, at great cost of time and money. But the engineers came up with an elegant alternative. They decided it would be cheaper and faster to move the bridge 30 centimeters from where it was originally supposed to go. Now the 3 remaining towers had to be placed precisely on the recalculated bridge line. The designers of the towers had faced a troubling dilemma. The towers needed to be strong so they could survive earthquakes. But the more a structure weighs, the more it is impacted by earthquakes. So to reduce mass, the pier shafts were built hollow. Engineers were able to inspect the hollow piers after the bridge was finished via an access just under the roadway. The stairs lead down, right to the bottom of the pylon head. From there, you have to take a ladder, and that leads to hundreds more stairs. But even this is not the bottom of the pier, it's just water level, where a door provides access for outside inspections and fresh air. After climbing down to water level, engineers still have hundreds more stairs to go, 520 before they reach the bottom.
So we're at the bottom of the pier. We're 200 feet below the sea level, and below the concrete is the seabed.
At these depths, it's not surprising that the sea tries to force its way in. It is surprising that there are crickets hiding down here. The doorways lead to empty air chambers inside the widest part of the tower foundation. Critical monitoring devices are mounted on the wall that will sound if they detect water. An accelerometer registers the slightest movements of the tower during earthquakes. To help the towers survive earthquakes, engineers came up with another design first. The towers are not anchored to the seabed in any way. They simply rest on top of the 3-meter thick gravel. This means that in the case of an earthquake, the towers will slide on top of the gravel, and the fiercest shaking will not be transmitted to the other parts of the bridge. Engineers calculated that the towers would be able to slide nearly 2 meters without compromising the bridge's integrity.
That was beneficial to the structure because when sliding, you were in a way cutting off the maximum stress in the structure.
With each pier in place, the engineers were now ready to build them another 164 meters high and hang 2,200 meters of roadway from them. The finished bridge was going to weigh far more than the towers did now. And this added weight would make the foundations sink into the seabed. But no one knew exactly how deep. It could mean disaster for the finished bridge. So the engineers had to force the towers to settle now by making them thousands of kilograms heavier. To do this, they used seawater to completely fill each pier. The plan worked, and the water caused the foundations to finish settling. Now engineers knew they would be stable when the bridge was completed. May 2002, 2 years to the deadline. Each tower was a major construction site, with barge after barge delivering huge quantities of concrete. The towers would rise from the surface of the water in 4 distinct sections, each critically important, each massively complex, and each an enormous challenge in itself. First was the octagonal pier shaft. This supported the pier head, an inverted pyramid that served as the base for the 4 pylon legs. The enormous legs met at the pylon head, which in turn supported a massive metal bracket where the cables were attached. The success of the entire bridge depended on the structural integrity of all these elements. But the engineers were about to discover that they had overlooked a dangerous weak link. Because the Gulf of Corinth covers an active seismic fault line, engineers had taken care from the start to ensure that the new Rion Antirion bridge was designed to withstand earthquakes. The most complex elements were the pier heads, 16 meters high with sides that widened to 40 meters. But when construction was well underway, new calculations revealed a dangerous design flaw. An earthquake would subject the narrowest point of the pier head to forces greater than originally anticipated. As currently designed, the bridge would not be able to withstand them. It was too late to redesign the tower, but not too late to increase the strength of the pyramid. The engineers added vast quantities of rebar, more than at any other part of the bridge, until inspectors were satisfied that the piers were strong enough. Construction was now able to continue as originally planned. The next stage of construction was an extremely vulnerable one. The engineers had to take extensive precautions while building the 4-legged pyramid. The completed pyramid would be rigid, but while it was being built, before the 4 legs converged at the top, the unconnected parts were dangerously weak.
In the middle of the strait, we have a fault line, and you have to take into account an earthquake while you are pouring concrete, while you are putting something down with a crane. So this is very difficult.
If an earthquake had struck during construction, the legs of the pyramid could have moved, crumbled, and crashed into the sea. Most structures need bracing during construction, but here the contractors took the idea to a new level. 4 massive cross girders braced the legs at 4 different levels, a total of 16 gigantic cross beams. It was an enormous amount of scaffolding to erect, and it was all temporary. It would be removed again once the pieces were in place. This took a massive amount of time, money, and materials, but it was an important insurance policy, one they hoped they'd never have to use. When the towers were finished, one of the 4 legs had a lift installed. But even with it, the journey to the top was still arduous. The lift didn't go all the way up. It stopped at the pylon head where the legs converged. The pylon head has one of the most important jobs on this cable-stayed bridge. It holds the 30-meter tall blue steel bracket that secures the cables. The entire load of the roadway is anchored here through the cables. These gargantuan towers rise 164 meters above sea level, almost as tall as the Washington Monument. But there's another 63 meters hidden under the surf, making the towers significantly taller. April 2003. There were still 20 months to the deadline, but a new urgency now arose. Greece was chosen to host the 2004 Olympic Games. If the bridge could be ready 5 months early, the Olympic flame would be able to cross it on its way to Athens. The builders pledged to make this happen. Workers fabricated the roadway sections on shore. The assembly process started with massive steel beams. It would take 186 deck sections to build the roadway across the Gulf of Corinth. The deck segments came off the assembly line ready to be installed on the bridge. They were already fitted with anchors for the cable stays and even guardrails for the pedestrian walkway. But first, they needed to be carried from the shore to the middle of the Gulf, and that was easier said than done. Each segment was larger than a tennis court and weighed 270,000 kilograms, and it had to be lifted into the air over water. To do this, engineers used a specialized floating crane called the tack lift. It could hoist the huge roadway sections 50 meters up, carry them to the bridge, and hold them steady while they were installed. Every day, work began at dawn. The tack lift would pick up a single section of roadway, then inch its way into the Gulf. This section was installed right next to the tower. Now it waited high above the water for the next section to be connected. As the tack lift approached the bridge, one of its Dutch crew relayed directions. The captain guided the barge closer and closer until the new section approached the existing roadway. Surveyors used a laser to ensure accuracy to the millimeter, but they encountered a problem. The wind was too strong, and even the tack lift couldn't hold the span steady. They had to wait for 2 hours. Finally, workmen were able to use a huge temporary brace to secure it in place. Another team bolted it to the existing roadway, and for a short time, this section became the end of the unfinished highway. Once the crane had backed away from the bridge, a cable was attached to each side of the new deck segment. The other ends of the cables were anchored to the bracket in the pylon head. Each cable was made of up to 70 strands wrapped in black polyethylene, and each strand was made with exactly 7 steel wires, each about the thickness of a chopstick. When the cables were installed, the excess was cut off and the bare ends given a special coating to prevent rust. It took 368 cables in all to hold up the 2¼ kilometer roadway. 40 kilometers of cable made from 4.5 million kilograms of steel. In the summer of 2003, there was just 1 year to go until the Olympic torch would cross the bridge. After relatively smooth sailing, builders now faced one of their biggest nightmares. A major earthquake struck the unfinished bridge. It was the 14th of August 2003. A quake measuring 6.2 on the Richter scale hit while the towers were still under construction. The creation of the enormous Rion Antirion bridge faced disaster. The towers were extremely vulnerable, and even worse, the shock hit as builders were installing a new section of roadway. Miraculously, no one was seriously injured. When the dust had settled, all parts of the bridge were still standing. The construction crews had dodged the bullet and avoided a major catastrophe. The unfinished pylons held together. The insurance of the expensive scaffolding and crossbeams had more than paid for itself. But this was just the beginning. Engineers knew that many more earthquakes were coming, so they designed the bridge with a unique safety feature. The entire roadway is like a giant swing. This means that in an earthquake, it can move freely, isolated from the most violent shaking. But the very design that protects the bridge in earthquakes makes it vulnerable to high winds. The challenge engineers faced was to build a roadway that would not rock in the wind, but would rock during a violent earthquake. To hold the deck in place in bad weather, designers created an innovative system of giant struts. In heavy winds, this main strut holds firm and prevents the roadway from moving.
But when we have something a little bit more extreme, like an earthquake or something which is a load over a certain limit, this is going to run out of action. It's going to break effectively. Inside, a small part is going to break, and the 4 dampers around it are going to take the movement.
The enormous dampers act like the shock absorbers on a car. They allow the roadway to move so it's not damaged in an earthquake, but at the same time, they keep it from swinging too violently or impacting the towers.
And the deck is going to move to side. It's going to absorb this energy of the earthquake, and we're not going to have a catastrophic event on the road or on the pylon. Yeah? So we're going to absorb the energy of the earthquake. It's important for the bridge to be able to move, so we need to let the deck move and absorb this movement with the dampers.
The dampers allow the roadway to move as much as 5 meters. In the event of an earthquake, it will be a rough ride, but the roadway should survive. Another difficult design challenge was predicting the behavior of the cables. All cables vibrate, but too much vibration would damage the bridge. So engineers here incorporated 2 technologies to help solve potential future problems. Although an untrained eye could easily overlook them, they are hiding in plain sight. Built into each cable is a collar. If the cables on the Rion Antirion bridge vibrate excessively, engineers can attach an additional cable that links each collar with the next. It's like muting a harp by putting a hand on the strings. Built onto the same cables is another device called a strake. This is smaller and even harder to notice than the collars. The strake is a spiral lip that runs the length of the white cable sheathing. It looks like decoration, but it plays a key role in the longevity and safety of the bridge. This was a lesson a bridge in Texas learned the hard way. The Fred Hartman Bridge in Baytown is not as big as the Rion Antirion Bridge in central Greece. The main span is 380 meters, not 2,200, and it spans a river, not the Gulf of Corinth. There is no active seismic fault line here, and no excessively deep water. So it was a surprise when the Fred Hartman's cables began to misbehave. And not just a little. The cables were vibrating so much they began to tear the bridge apart. The vibrations would come and go, and the reason why was a confusing mystery. In good weather, there were no problems. In high winds or in pouring rain, there were no problems. But mild rain and a mild wind coming from just the right direction spelled disaster. It took endless observation and wind tunnel tests to work out why. It turned out that in mild rain, a tiny stream of water would run down the cables. The water would change the profile of each cable just enough for the wind to set it in motion. However, if there was too much wind, the water would be blown off the cable. And if there was too much rain, the stream of water wouldn't form. But the designers of the Rion Antirion bridge didn't have to worry about mild wind and rain. Rainwater wouldn't be able to run straight down these cables because of the simple raised lip that spiraled around them. By spring 2004, the new early August deadline was fast approaching. If the Olympic flame was going to cross the bridge, all the deck segments would have to be in place. In May, with time to spare, the tack lift transported the last section of roadway from the staging area to the bridge line. The contractor's efforts finally paid off. Greek authorities saw the Olympic flame cross their spectacular new bridge. A week later, the bridge opened to traffic, 4 months ahead of the original deadline. For the contractor, it meant a bonus for opening early. But work on any bridge is never really finished. The builders just switch gears from construction to maintenance. To access the sides and underbelly of the bridge, inspectors used motorized scaffolding called a gantry. But checking for rust is still a high wire act.
So we have to inspect all the bridge every year. All the yellow paint has to be inspected from one end to another. It takes about 3 weeks just to inspect all the yellow, each bolt and each yellow coated area. So here we'd have at least 400 bolts, maybe more as we go closer into the middle of the span. These were all placed and tightened in one day, or at least in a shift of 8 hours. These need to be checked carefully at the gaps and around them to see if the paintwork is maybe showing some signs of weakness. It's not easy to inspect all the structure while it's being constructed. There's bound to be a few little points which have been left behind, despite the thousands and thousands of inspections which have taken place during the construction. After a full day checking yellow, you don't want to see it again, I'll tell you.
Maintenance on this superstructure is never routine. Teams need special training and physical strength to access the far reaches of the bridge. From the top of the towers, the view is spectacular. But working in good weather here is not a luxury. It's a safety requirement. Even a small mistake could be deadly. These daredevils are called alpinists, as in mountain climbers. They're specialists in bridge maintenance, flown to Greece from France by the bridge construction company. These alpinists can get to places that barely qualify as places. They anchor their safety line by drilling a single hole, where they pound in a single bolt, then attach their rope to a single loop.
10 years of this job, and I'm still scared up here.
When the alpinists reach the cables, they hang from rollers. If they spot a place where moisture might be able to penetrate the covering around the cable, they dab it with cork. Generally, they start at the top and work their way down. They can spend up to half a day at a time suspended above the bridge. They repeat these trips for months until they've checked all 368 cables. Everything that happens on the bridge, day and night, is supervised from the command center behind the toll booths. Operators can see everything that's going on.
Can you please check for that stopped car? Use the 52.
But more importantly, they can monitor the vast network of cameras and sensors installed all over the bridge. There is too much information to watch all at once, so computers help by constantly evaluating the cameras and data. When a computer spots potential trouble, it alerts operators. If there is a situation on the bridge, operators can quickly reprogram signs to warn drivers. The Rion Antirion bridge faces a combination of challenges that no ordinary bridge could survive. Strong earthquakes, exceptionally deep waters, fast currents, and weak seabeds. And added to these dangers are the risks that every megastructure faces. One of the most heart-stopping of these is lightning. A single bolt can wield 1 billion volts of electricity and reach a vaporizing 30,000 degrees Celsius. Lightning loves metal and seeks out the highest point around, so bridges are often a prime target. The designers of the Rion Antirion bridge kept this in mind. A bridge's best defense against lightning is a lightning rod. This provides a path of least resistance for the lightning. On the Rion Antirion bridge, rods are connected to metal ribbons that guide lightning bolts around the bridge and down to the sea. An electronic monitor on the tower records each time lightning strikes here. The engineer slides a magnetic key and a red light flashes once for each strike since the device was installed. The lightning rods have worked successfully many times, but on the 27th of January 2005, a massive bolt scored a direct hit to one of the cables. Operators immediately closed the bridge. 40 minutes later, the cable fell to the deck. It had been burned completely through. Losing one cable was not dangerous. This bridge was built so mightily it could handle losing 2 or even 3 cables without a problem. 3 days after the freak lightning strike, the damaged cable had been replaced. The bridge was as good as new and open for traffic. The quick repair was yet another triumph for the builders of this mega structure, and it remains a source of pride for everyone involved.
I was really lucky because I worked during the construction. when I talk about the bridge to my son, that, you know, your daddy built it, you know. And I hear it from him sometimes. He says, let's go to the bridge, my daddy's bridge, you know. And that makes me really proud.
Before its construction, the European Union designated the Rion Antirion Bridge one of its most urgent projects. Today, the bridge has changed the geography of the region. Transportation and commerce have been enhanced across Greece and all of Europe. More than 100 years after the Greek Parliament proposed building a bridge here, and only 5 years after construction began, this bridge entered the record books. It is the longest cable-stayed suspension bridge in the world, with the longest fully suspended continuous deck, 2,200 meters. It has the world's largest bridge foundations and the deepest, sitting 60 meters under the sea. Innovative engineering allows the Rion Antirion Bridge to survive where other designs would fail. It stands as one of the world's mega bridges.